Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. This is video number 49 and I'm going to discuss the Joule Thompson Throttling process. I'd like to draw your attention to my website universityphysicstutorials.com. So the Joule Thompson process is sometimes conceptually difficult to understand. I had trouble understanding it at the start. I think I'm going to try and teach you or explain to you how I understand it or my understanding of it, and hopefully that will help. So it's very useful, and the reason it's useful is because it cools a gas or a liquid, but usually we're talking about gases. And where is that useful? It's useful in refrigerators, and let's say if you're talking about pretty advanced chemistry or physics, you're often going to be talking about trying to liquefy gases. So we're trying to, like, you might want to try and liquefy helium, for example, or hydrogen or whatever. These are all important things which you've done in the past, and this Joule Thompson throttling, or the Joule Thompson way of cooling a gas, is something which is very important. Now you might think that adiabatic cooling is a contradiction in terms, because surely adiabatic by definition means that there is no heat change. That is correct. However, I suppose I better tell you up front what actually happens is that it's adiabatic, so Q is 0. However, if we look at the internal energy of something, the internal energy can usually be kinetic energy, or it can be potential. Let's say I'll draw P for potential energy. Now, the temperature is related to kinetic energy. Okay, we know that. So if you want to keep your total energy constant, but if somehow you can reduce the kinetic energy, what will happen is your potential energy term will go up. So if you increase your potential energy, your kinetic energy will go down, and as a result your temperature will go down. And that's actually what we're going to do, is we're going to convert some of our kinetic energy into potential energy, and as a result we're going to cool down the molecules or make them go slower, which is the same thing. They are all different ways of saying the same thing. So let's imagine we have a tube here, okay, cylindrical tube, and in it we put our gas molecules in green, and we put two pistons, one at either end. Note the direction is left to right as you look for both pistons. Now, I'm going to define the area here in blue as my throttle. Okay, I'm going to this kind of oval around it. So, but this is small in comparison with everything else, because to be honest, you actually don't use pistons to do the throttling process. It just happens automatically. But I think it's easier to conceptually think about these pistons. But they are there, but I suppose they're a lot far. They're much further from the throttle than the size of the throttle itself. So let's look at the first law. So the first law says that the change in energy is Q plus W. Change in internal energy is Q plus W. But we're talking about an adiabatic process, so Q is equal to 0, and then we get delta U is equal to the work done. So this is the change in the internal energy. So what we're going to talk about here is, this is the initial state over here, this is the final state. So what we're going to do is we're going to push with this piston very slowly our gas molecules through a porous material, a porous mesh, and they're going to come out here into this area here, and we're just trying to ease them through it nice and slowly. The very important point, the crucial point here, is that the intermolecular separation here is getting larger. So here X is going up. Say here X is, let's say small, let's say for argument's sake, the intermolecular separation is small, here it gets larger. And by definition, if the intermolecular separation is getting larger, then the pressure is going to go down. These are all important things that you should remember. So going back to the internal energy. So that means what we have is the internal energy of the final state minus the internal energy of the initial state is equal to the compression work. Well, I've done a video on compression work in the past. You can look up my videos if you like, and you'll find that it's just going to simply be P pressure initial, volume initial, minus pressure final, volume final. Simple. So let's arrange for the final and the initial variables, and we're going to get PF, VF plus UF is equal to UI plus PI, VI. Now, I hope that you will realize that what we're actually looking at here is the enthalpy, because the enthalpy H is equal to U plus PV. So it's the internal energy plus the energy required to make room for your system. I think that's video number 8, but I'm not too sure. So what we're really looking at here is an isenthalpic process where the initial enthalpy is equal to the final enthalpy. So by definition, our Joule Thompson process is isenthalpic, and that's the condition upon which everything works. Now, just as an aside, an ideal gas could never work for the Joule Thompson process because H is equal to U plus PV. Using the equipartition theorem, we have half NFKT. F is the number of degrees of freedom, of course. And we're also going to have the ideal gas law, NKT. So that's going to be just F plus 2 over F times NKT. That's the enthalpy of an ideal gas. Sorry, that's a factor of 2 here. But the problem here is that if it's isenthalpic, it implies that the temperature is constant. Constant enthalpy implies constant temperature for an ideal gas. Okay, but as we'll see in a moment, that's not what we want, and it's precisely because it's not constant temperature that we get this cooling. All right, so next we need to work out why there is cooling if it's isenthalpic. What's happening as follows: is we have H final is, or we'll say H initial. H initial is equal to H final, or U initial plus we'll say, how do I put it this way? Yeah, U initial plus P initial V initial is equal to U final plus P final V final. Now, the internal energy, of course, is going to be, how do I put it? I'm going to write it this way. The internal energy can be thought of as being both potential and kinetic. So we have the kinetic energy associated with the initial plus the, let's say call it kinetic, we'll call it T, and we usually call, let's say, potential is usually U. I'm going to call the potential energy U still for argument's sake, so say UP. And we're still going to have PI, VI. I'm hoping that the notation isn't going to confuse you. So then we're going to have the kinetic energy final plus the potential energy final is going plus the final pressure plus multiplied by the final volume. Alright, like that. So what we're really looking to do is just analyze how does the kinetic energy somehow get converted into potential energy. So we need to look at our van der Waals model, something which I discussed in the last number of videos. So we know that there are different types of forces. We'll say there is a positive attractive force and there is a repulsive force. So this is attractive and this is repulsive. Okay, I don't know why. Yeah, so they're attractive. So under most conditions, the attractive forces dominate because the attractive forces we'll say the attractive forces are weakly attractive. Okay, they are weakly attractive at long distances, and these ones are strongly repulsive at small distances. Okay, we know that. So usually the potential energy term dominates, and this is the attractive. So the potentially, excuse me, usually the potential energy term is negative. Okay, so what I'm going to do is, when it's attracting, we're going to give it a negative sign, and when it's repulsive, we're going to give it a positive sign. Usually the potential energy is attractive because usually we're talking about long distance forces, and as we will bring the molecules closer and closer together, it becomes repulsive and it changes sign. But if you think about it, if the potential energy term is for long distance, that means we'll say two molecules which are closer together. Let's say for argument's sake, the potential energy term was equal to 1. But then if we brought them further apart, their potential energy term will now be greater than 1. So as we separate them, or as we increase the separation, we increase the potential energy term. But increasing separation is the exact same as decreasing the pressure. So as we decrease the pressure, we increase the potential energy term. Okay, that's what happens. So going back up here, so we know that it's an isenthalpic process. But what we're saying here is that the volume or the pressure, we'll say, of the final state is going to be lower than the pressure of the initial state, and as a result, the the potential energy term is going to be larger. So what's after happening is the kinetic energy term of the initial is greater than the kinetic energy term of the final, and the potential energy term of the initial is going to be less than the potential energy term of the final. And this means that the temperature initial is going to be is going to be much greater than the temperature of the final state. So your gas is after cooling down. And that's exactly how it works. So what we do is we get essentially a tube. We put it through we put it through a throttle. Let's say often it's just a mesh. We just ease it through the mesh with the pressure. The separation between the molecules increases. The pressure goes down. Because the pressure has gone down, the potential energy term goes up and the temperature goes down. So there's a lot of ups and downs. And that's how we cool. So for example, when people are trying to cool hydrogen, that's one of I think actually when they're trying to cool hydrogen, they used the Joule Thompson cooling. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also click on universityphysicstutorials.com.